Hello and welcome back. Before we start today's content, I thought I did a quick recap on what we did last week, which is polymer and addition reaction and addition polymerization. So you probably don't have to write any extra notes. If you should already have all of this written down if you watched last week's videos. But this is a definition of a polymer that you can use. So a polymer is a substance composed of many small covalent molecules, and these small covalent molecules are called monomers, and they are joined together covalently. So the analogy that we tend to use when we talk about polymers is beads on a string. So if you have beads, you can think of each bead being a monomer and you join them together. So obviously the analogy breaks down because you don't actually have a string in the first place. The two beads will form their own string. That's where the analogy breaks down. But you can have multiple beads on a string. Each of these is going to be a monomer, and you're going to have this being the covalent bond. So it's very, very important for a chemistry student to understand that the link that connects multiple monomers together in the case of a polymer is a covalent bond. So it's fairly difficult to break. You definitely cannot break it easily with heat. So it's not as weak as, say, hydrogen bonds or dispersion forces or dipole-dipole interactions. Covalent bonds are really, really hard to break. The process of making a polymer is called polymerization. And I do want to point out one major difference between a polymer and any other covalent molecule. And that has to do with the third thing here is that when you change the type or the order of the monomers, that would allow a new polymer to be formed. So if I draw the same thing again, let's say I only have 4 things or maybe 6 things. So if it looks like this, they don't look very different, but I can definitely just vary if I just do like different colors for different monomers. So let's say this is the first type of monomer, and then you can have perhaps red maybe. So you can, if you change the type or you change the order or both, you change the polymer that is formed. Sometimes the order doesn't make a difference, but we're going to look into that in more detail. So in the case of addition polymerization, changing the order actually doesn't change the polymer at all. You need to vary the size, but there are other things that you can do. So you can have 2 of the same types, that's fine. But you basically can have a variety of polymers from the same building block, and that's one of the unique things when it comes to polymer. I think anyone who is doing biology would know this really well because all the macromolecules that you are learning except for lipid, so proteins, carbohydrates, and DNA and RNA, they are all polymers. So those molecules, which even if you're not doing VC biology, I'm sure you've heard of before, you probably shouldn't do that. But all of those molecules, all of those macromolecules are polymers, and they are naturally occurring polymers. And they're not the only types of naturally occurring polymers that you can have. You can also have things like cotton, which is a naturally occurring polymer. However, the word plastic, which we're going to use, and I think I try my best to not do it, but I probably will, is I tend to use the word plastic and the word polymer interchangeably in this topic. And the reason for that is because plastic is essentially a general word for any synthetic polymer, so any man-made polymer, which I guess synthetic is a better word because I make my own proteins. But anyway, my body does. Synthetic polymers, any synthetic polymer is going to be called plastic. They try to change this. They try to come up with another name beside plastic. I think they could settle on pucca, which pucca like Pucca, but I don't think this name stick at all because the only pucca that I could find when you Google the word is the cartoon character, so I don't think it works. But there is a reason for it. Maybe we'll talk about it later. There are 2 ways to make polymers. You can have addition reactions. So it will produce addition polymers, which is what we looked at last lesson, or we can have a condensation reaction to produce condensation polymers. We haven't talked about condensation reactions in chemistry. I know the biology pupils surely have heard of it, but we're going to look at this next week in a lot of details. Maybe I ask one of the bio people to lecture it for us. We'll see. Okay, so addition polymers are formed via addition polymerization reactions, it is absolutely essential that the monomers are alkenes. Actually, they can be alkyls, but we don't look at it. But they have to contain at least a carbon-carbon double bond or carbon-carbon triple bond. But we really in VC only look at the type when you have a carbon-carbon double bond. And when the monomers join to each other, the double bond converts to a single bond. So you're going to break, basically you're going to break one of the bonds in the carbon-carbon double bond. And when you do that, you basically create two extra openings, if you will. So this is just any addition reaction is going to do that. But in the case of an addition polymerization, this opening is going to be used to connect to another monomer. So the second pair of electrons previously in the double bond are used to form covalent bond. Yeah, so you can form one covalent bond on this side and one on the other side. A good thing about addition polymerization is that you're going to produce no byproduct, and that's the nature of any addition reaction. You add all the reactants together, so you go from multiple reactants to one product. That's how you know it's an addition reaction. Only one product is formed. Well, we're not going to go into the nuts and bolts of addition polymerization as a chain reaction because there are so many other things that will take hours and hours to talk about, so I'm not going to, and you don't have to know it at this stage of your chemistry career. You can learn about it later when you go to university, I think. But I want to use that to talk about addition polymerization of propene in, again, I'm sure you had to do it for one of the examples, but if the question ever asks you to write addition polymerization of propene, your first step is probably to draw out propene, and I hope you are able to do it at this point. Let's just go with, okay, let's go with structural formula. Not my favorite, but it just takes forever. Okay, so this is propene, and whenever you need to write an addition reaction in general, and specifically for addition polymerization, it is important to shift your focus on just where the CC double bond is, because that's where the addition reaction is going to take place. So specifically for a polymerization reaction, I'm going to convert this into this form because essentially I'm only interested in the CC double bond, and everything around it I'm going to flip up or down. So I'm going to turn it in, oh actually we follow this in the CH, there's a H here, it's a CH recipe on this side. Okay, everything around the CC double bond I'm going to flip up or down, so effectively turning it into a branch. Okay, so when you have the monomer in this form, it's actually very, very easy to know what happened to the monomer to turn it into a polymer. You basically break one of the bonds in the CC double bond. Let's just write the process. When you get to year 12, you have to remember a few other things on catalyst and condition and temperature, and but not yet, not yet. So addition polymerization is a process, just in case I don't remember. And you basically break this part and then have it here. So this part is going to connect with another monomer, and then it keeps repeating. So one way to write the product is you just need to write one monomer, because this polymer is made from one type of monomer only, and this type of monomer, this particular section is going to repeat multiple times. So you just need to tell me that this is the section, and you just need to put an N here to show that it is repeating. So if you draw the product in this form, this is essentially the formula of the polymer. So this is the formula form. It is very important that these bonds go out of the brackets just to show that it's going to repeat. But even if you don't, I think actually try to do it. So the product is polypropene. Okay. Now I do want to show you another form. Okay, so this is the first one. This one I just drew before. So this is when you show the formula. But there is another way that you can draw, and I wouldn't do it unless the question specifically asks for it, and that is this form. This is when the question asks you to draw a section. Most of the time, if the question asks you to draw a section, it is going to specify how many monomers in the section you're supposed to draw. So this example is a section of 4 monomers. And you can tell there are 4 monomers because there are 8 carbon atoms in the backbone. So this is the first monomer, and then this one, and then this one, and then this one. So 4 monomers. If the question doesn't specify, you can just put the CH3 ion, any locations really, just as long as you have one CH3 per monomer and no more than that and no less than that. The other thing you need to keep in mind is if the question asks you to draw a section, then you need to make sure that you have open ends. So you don't have a bracket, just have open hanging ends on either side. Sometimes people do ... on either side just to show that it continues before and beyond what is shown here. But you'd have to make sure at least that you show the open ends. If the question asks you to draw a section, I think you do need an open end if you draw this as well, but definitely if you draw a section, because a lot of time people just stop here. That wouldn't make any sense. It becomes just a molecule and not a polymer anymore. So that's just a quick recap of addition polymerization. If we go back to our flowchart and the production of the N95 mask, so now we actually understand how to go from propene to polypropene. And what I really want to talk about in this video is what happened after this. So what if now I have, so propene, just this is propene. If you do skeletal formula, so propene is made from propane, which is here. We don't need to worry about this reaction. And now you have polypropene, which normally we don't use. Well, we don't really use skeletal formula for a polymer, but let's just say you have like a chain and then it has CH3 up and down eventually. So you have one of these, but how did you go from here to the product? And I also want to point out that polypropene can be used to make a variety of plastic products. So it's not just for the N95 mask. It's actually used a lot in a range of hygiene products. Diapers is a popular example, and the reason why I bring up diapers is it's also highly disposable. Like you definitely cannot reuse it, and that creates a lot of issue later on. But you could also use it in packaging, so it can be used to make this. It looks like cling wrap, but it's a little bit harder. So it is used in, say, the packaging of, I don't know, cosmetic products, for example. If you buy lipsticks, you can see there's like a package outside the lipstick. I don't know why any of you would buy lipstick at this point. Anyway, and then plastic lids, plastic bottle lids. This is one of the most common use of polypropene, but there are other uses as well. So the question is, how do you go from one raw material to multiple products? What are the steps to diversify these raw materials? So that's what we're going to talk about in this video. So the agenda is to describe and explain the differences in properties of polymers. And I think I kind of already give away the answer here by varying the chain length, the degree of branching, and the addition of plasticizers. So there are 3 ways that we're going to look at that allows you to go from one raw material to multiple products. And then we're going to look at one more way, so 4 ways. Okay. So before we get to that, there is an extra step that has to happen to go between polypropene and the products, and that is the production of polypropene pellets. So you don't, normally what happens in the industry is the people who make the plastics don't necessarily make the polypropene themselves. They would purchase the polypropene from another supplier. And so the polypropene is going to get packaged and then sold in the form of pellets. So what happens is once you make the polypropene from the addition polymerization reaction, you're going to melt it, so make sure that it is in molten form. And molten form of polypropene just means that you have the chains, they're pretty far apart because you're going to have very weak, very weak dispersion force between them because the temperature is very high. So this is weak dispersion forces. And the molten polypropene is going to go into this machine. I could not find a better diagram. Well, I found one diagram and the rest are just the actual pelletizers. I don't even know how to pronounce the word. But anyway, you don't really need to know too much about this, but just know that the molten polypropenes come in and then there's this machine that's going to cool it down, put it into molds and then cool it down really quickly. And when you end up, in the end, it's going to be these pellets. So they're basically solid form of polypropene. So you still have the chain but they're just a little bit closer to each other, so they're solid, and you have a little bit stronger dispersion forces between them. But these are the pellets. Somebody told me that they kind of lentil in size, so I put that there. But these are the polypropylene pellets. They're made by pouring molten. Yep, so that's just what I said. And about lentil size. So I'm just going to stick with lentil size. So these polypropylene pellets will then be shipped to different factories that use polypropylene to produce different plastic products. And a lot of the time they are shipped internationally. I think a lot of the companies that make these pellets are in China. Apparently you can order them from Alibaba. I was looking at it the other day. Now there are a lot of problems with plastic pellets for those who haven't heard of plastic pellets or know that there are problems with plastic pellets, because first of all, they are very similar in size to fish roe or fish eggs. So if they for some reason get spilled into the ocean, it is very easy for organisms to mistaken them for food, especially the organisms actually eat these. So this is a diagram of noodles is another name. I don't know why. Whenever you research on this topic of plastic, everything has like 5 different names. But essentially, they can end up in the systems of organisms that mistook them for food and ate them. And it is extremely difficult for these organisms to get rid of the now polypropylene or whatever other plastic pellets that are in their system. And you might wonder how come these pellets end up in the ocean. And there is another very good diagram that shows this process. And essentially you can spill it pretty much anyway, especially if it is transferred internationally. So if you start from oil, which we talked about before, so you can probably make the noodles very close to where the oil rig is, because you get your crude oil and then you get your propane and then your propene and then your polypropylene. But then it can spill in transit, then it can spill in more transit. So you go from the production of the pellets to the factory, and then it can spill. And then sometimes it's spilled, if it's shipped around the world, it can spill at sea, it's lost at sea, and it's extremely difficult to recover if you spill it in the sea. So there are a lot of issues with packaging the raw material into this form. It is quite easy to use. I think that's the reason why they package in this form. But anyway, so there's that. But anyway, let's just assume that we actually managed to ship the pellets to the factory. So now we need to go from the polypropylene pellets to the actual material, N95 mask or anything else. So how do you vary the property of polypropylene based material from the same starting material? Given the same monomers, the physical properties of a polymer can be altered by generally 2 things. If you don't want to change the nature of the polymers, you can either vary the length of the chain, or you can vary the degree of stacking between the chains. And let's talk about the first one, varying the length of the polymer chain. All right, a longer polymer chain would contain more electrons, and the dispersion forces between the chain would be stronger. This means that the material would have a higher melting point. So once you start with the pellet, you can, and then the pellets get shipped to the factories, what you can do is you can actually cut the chain. So these pellets can have like a very specific chain length already. So once again, you can produce more than one types of pellet. But you can make the chain longer, or you can, by joining multiple pellets together, if you will, or you can cut them so you have a lot of shorter chain. Okay, I'm going to try to make sure that the size match overall. So you can have shorter chain like this, for example. And essentially, let's make it even shorter. Essentially, if the chains are shorter, then you would weaken the dispersion forces between the chains, because if you have shorter chains, you're also increasing the distance between them. So this one is going to have stronger dispersion forces, the one with longer chain length, so stronger. And it doesn't even have to be dispersion forces. I know we've only talked about hydrocarbons and everything is non-polar so far, but later on when we look at other types of polymers that have a polar group, you could have dispersion force, dipole-dipole interactions and then hydrogen bonds. And the closer the chains are, the stronger these bonds are as well. So this one in general will have stronger intermolecular forces, which generally means that it is going to be more rigid, it's going to be harder, it's going to have a higher melting point, and it really depends on what you want, what kind of properties you want out of your product. You may want that. So stronger intermolecular forces here. All right, so I think I discussed how you could potentially control the chain length here. You can control it during the manufacturing process by determining when to terminate the addition reaction. So you can make pellets of different lengths as well, but then you can just buy the same pellet and then join the chains or cut the chains later. So there are two ways that you can control the chain length. This is very, very specific, so I'm not even going to tell you what chain length is in the N95 mask because there are 4 different types of polypropylene plastic in there. I think I have a slide later I talk about that. The more interesting thing is to vary the degree of stacking, and we talked about stacking last week, the week before, I think last Monday, we talked about stacking in the context of a branch and how that affects the boiling temperature of molecules of the same size. We're going to talk about that again today, and there are a few more terms to say the same thing because I don't know who came up with this. Anyway, so when we talk about stacking in the context of a polymer, what we tend to refer to is crystalline regions. And these are regions that are created when the chains are lined up in a regular arrangement, which is another way of saying that they can stack closely together. Here's a visual representation for you. If you remember when we talk about ionic lattice and the word crystal was used to describe regions of regular arrangement, this is very, very similar. It is also used to describe regions that had a regular arrangement, but a regular arrangement in a polymer is made by regular stacking. So that's a crystalline region. And obviously, if you can have regular stacking, you have very strong intermolecular forces, mainly dispersion forces between the chains or between sections of the same chain. If you have a very, very long chain, they can start folding as well, which is, I think, what is going on in this case. You just have one giant chain that folds. Now, another interesting feature of a crystalline region is because it's so tightly packed and quite dense, it's going to prevent the transmission of light through the material. So if you're going for an opaque material, you want to introduce crystalline region for that purpose. You want to introduce crystalline region for that reason as well, because light cannot pass through if it's really tightly packed. Anyway, conversely, on the other side, I can't even speak English today, but you have amorphous region. There's so many words. Essentially, it's when you have a random arrangement. This is the opposite of crystalline region. The chains are randomly tangled and unable to pack very closely. So obviously, you're going to have weaker dispersion forces between parts of the chain. You can also have more than one chain. But the good thing about amorphous region is it allows light to go through, which means that you can have a transparent material. So again, it really depends on what material you try to make. Do you want it to be transparent or do you want it to be opaque? Do you want it to be softer or harder or more rigid? The other interesting thing about a polymer is you don't need to, and I think most of the time you don't have a polymer that is 100% ordered or 100% random. It's normally you have part of it that's a crystalline region and part of it that is an amorphous region. So you can control the percentage of the polymer that is crystalline, and that will affect the level of hardness as well as the level of transparency that the material can have. And by varying the percentage of these two, you can create a really wide range of materials from the same starting material. I used the word material twice in the same sentence. Again, I really cannot speak English this morning. One more way to actually let's go back and talk about exactly how you can make sure something has a crystalline region rather than an amorphous region. And that is by controlling the positions of the side groups. If you go back to, because this is polypropylene we're talking about, there is a side chain if you think about the polymer. So the monomer is just a CC double bond, but there is a CH3 that now becomes a side chain in the polymer. So this is what it looks like. Probably should draw the rest of the H. I think there's some words that's going to appear here soon. But anyway, the positions of the side chains could significantly affect the ability of the chains to stack and the formation of crystalline regions. Again, we've talked about this last week, where the position of the side chain, it's going to affect how easily something can stack. In general, there are three ways the side chains can be positioned, and you have to control this during the polymerization reaction. It's actually incredibly complicated. I learned about this when I went to uni later on, but there are generally three ways. The first one is isotactic. As you can see, the side chains are on the same side for every single one of them. Second way is atactic, so they random, and syndiotactic, which is when you have a pattern. So it's not all on the same side, it's not random, it has a repeating pattern. So let's look at the first one, isotactic. Isotactic, as I just mentioned, is when all side groups are on the same side of the polymer. And stacking can occur fairly easily if the polymer is isotactic, because you can probably stack this chain and then the one below it quite closely to each other. You can form dispersion forces between them. So this is, ooh, what is that? This is dispersion forces. So you can create a material that is fairly rigid and opaque because of close stacking. So isotactic is a way to achieve crystalline regions in your polymer. Alternatively, you can have atactic, is when you just randomly distribute the side chain. So sometimes it's up, sometimes it's down, but there is no pattern. And that is going to prevent any close stacking. So you actually have weaker dispersion forces between the chains here. Weaker dispersion forces. So you're not going to be able to form crystalline regions if your chain has an atactic arrangement. The last type is supposed to be the best, but it's actually quite hard to achieve, and I think people are still doing research on how to make a polymer chain that is syndiotactic, and essentially you have a pattern. In this case, it goes up, down, and then up, down, up, down, up. It's supposed to give you the best stacking out of the three, but still, it's very hard to make, unfortunately. So that's the issue with it. But it can be even better than isotactic in terms of creating a crystalline region. You don't have to worry too much about syndiotactic though. It's mainly the other two that is actually being used widely in the industry. I need to fix this photo. Anyway, so that's three types of stacking. So if you control the positions of the side chain, you can achieve different degrees of stacking, and that's one way to control the physical properties of materials. Now, if that doesn't work, there is one more thing that you can do to control the degree of stacking, and that's by adding plasticizers. I'm not going to go into any example of any plasticizers. There are just way too many, and they do different things as well. But essentially what they are, plasticizers, is, well, they are molecules to make the material more plastic-like. And in this sense, the word plastic is used to indicate being softer and less rigid. So they are small molecules that can be added to polymers during their manufacturing process to force the polymer chains to be slightly further apart from each other. So they are molecules that are added to prevent close stacking. Let me just write that here. So you want to prevent, whoa, close stacking. So this is an example. Let's say you have these chains and they can't really move in relation to each other. So they because they stack quite closely, and plasticizer is, if you add them, it's going to allow the chains to be able to glide on top of each other. They're not very close to each other, so they tend to be softer if plasticizer is added. That's all you need to know. You don't need to know any specific examples. What kind of bond is formed between the plasticizer and the chain? Probably some intermolecular forces as well. Again, it depends on the types of plasticizers. Is that it? Yep, that's it. So if we go back to the N95 mask, or any medical mask for that matter, Most of the time, you actually don't have one type of polypropylene plastic fabric that is used to make the mask. So if you look at this, there are actually 4 layers within a mask. So the top and the bottom layer, I think, are actually made of the same material. So it's one type of polypropylene. It's called non-woven polypropylene. But then the filter layer, which is this is where all the action happens, if you will, is another type of polypropylene. So this is the first type of polypropylene material, and then you have the second type. And this one, the support layer, oh, this is acrylic, so it's not polypropylene, but you can also make it from polypropylene. So within the same mask, you can have more than one type of polypropylene fabric that is made by varying either the side chain or the chain length or adding plastic sizes. Now, specifically for N95, I think this is the filter layer, and what they do is they want to achieve something else, which is you want to have a lot of random arrangements. So if you assume, I don't think each of these is an one chain, but it's very close to one chain. So you want to have this really random amorphous arrangement of the side chains. And the reason for that is because this will trap any particles that is above 0.5 micron. So at least 95% of them anyway. So you want this random arrangement, not because you want the material to be harder or to be softer or more flexible, but because you want to create a barrier to trap particles. So again, you can vary the chain length and the arrangement to achieve other purposes beside the hardness of the material. Okay, there is one more thing that you can do. This has nothing to do with the N95 mask. The N95 mask doesn't use this. Again, can't speak English today, but I'm not making another video. But the other thing you can do is you can change the structure of the polymer to create what is called a copolymer. I cannot remember whether I talked about this or the video talked about it last week, but I'm just going to tell you again. So when it comes to a polymer, regardless of whether we're looking at addition polymers or condensation polymers, there are two types of polymers that you can look at. A homopolymer, as the name suggests, is a polymer that is made from one type of monomer. Or you can have a copolymer, which is made from more than one type of monomer. I mean, the name's quite obvious, I think. So these are some examples of copolymers. So once you introduce an extra type of monomer in the mix, there are so many extra things that you can do in terms of varying the properties. You can have block copolymer, or random copolymer, or graft copolymer. You don't have to remember these names. I'm just saying there are so many ways that you can arrange the types of monomers, and that introduce extra intermolecular forces, if you will. Is going to vary the strength, the type of intermolecular forces, and that affects the physical properties of the product. Most of the time, polypropylene copolymers are not widely used, but sometimes they are. If it is a polypropylene copolymer, then they generally consist of primarily propene monomers, and then you add a small amount of another monomer, and you can vary the property depending on what the second or even third monomer is going to be. So I'm just going to give you an example. Let's say I have CH3. So this is propene. So this is my primary monomer. And I have a lot of it. And then I have a small amount. I'm going to use ethene. So let's say this is a copolymer that's made between ethene and propene. So this is ethene. I don't know how many of this I have. Let's just say you have an amount of M, and M is smaller than N, because I'm a maths teacher. So you can have addition polymerization with here. Let's just create some more space. You can have addition polymerization between these two, and again, the production process is going to control how and how often the second monomer, the ethene monomer, is going to be added, and what arrangement you want it to be. But you can have a very, very random arrangement, which is what I'm drawing here. So the first one is polypropene, the second one is ethene, and then we can have another propene. Let's say we're going to bring it up like that. And let's say we have another propene here. So this is one example of a copolymer. I'm doing a section of 4 monomers. And you can tell that it is a actually, I think I have to tell you that it's a copolymer, but in this case, this is the first monomer, and then there's another one, and then there's another one, there's another one. It becomes more difficult if I give you a chain and ask you, is it a copolymer? But that's another story for another day. So that's the last method, not used in the N95 mask, but can be used to vary the properties of materials from the same raw material. All right, so that's the end of this mask, I guess. Well, there's one more thing we need to talk about afterwards, and you don't have to worry about this reaction, but let's say we start from trapped crude oil. This is your starting material. This is your fossil fuel. And then you're going to extract it to get to crude oil, go through fractional distillation to get to propane. Propane's converted to propene, additional polymerization to get to polypropene, and then you have to convert it to pellets. And normally, like I think I skip a few steps here. There's definitely transportation if the pellets are not made at the same site as the production of N85 of the mass, which I don't think it is. But you can go through a variety of extra modification by varying chain length. So you vary the chain length, or you vary the arrangement of side chains, side chain arrangement, or you can add plasticizer. Or we have so plasticizer. You can do either of these three things or all three, and that will give you a range of polypropylene fabrics that you can use to make your specific products, such as the N95 mask or anything else. I think that's the end of this video.